All right, so one of our applications to our vectors is with the concept of static equilibrium. So think for an object to be in static equilibrium, it means it's still and it's at rest, okay? Now that means if there are any vectors, force vectors that are acting on that object, for it to be at rest, the sum of those vectors has to be zero, meaning the resultant force vector is the zero vector, all right? So we have a situation here where this static equilibrium applies. A box is being suspended by two cables that are attached to the ceiling. The box has a weight of 1,200 pounds, and each one of those cables has a tension associated with it. We want to figure out what are the tensions of those two cables based off of the angles that are in the diagram there. All right, so notice you can think of the ceiling and the top of the box as parallel lines, because I think we would assume that the ceiling is flat and the top of the box is flat, right? So they're going to be parallel to each other, which means the two cables are transversals. They're transversals that are cutting through the two parallel lines. What that does is it creates alternate interior angles. So if I'm saying this is 45 degrees, then that other angle below is an alternate interior angle to that. It has to be 45 degrees as well. So just a little bit of geometry is being utilized here, okay? Now, there are three forces acting on this box. We're going to transfer this into a coordinate system. All right, so the first force vector is going to be from the right cable. And I'm going to call that vector F sub 1. And with respect to the positive x-axis, the angle is 45 degrees. All right, now the magnitude of that force vector is what we're trying to figure out. It's the tension within the cable. So I'm going to use T sub 1 to represent that magnitude, just so I don't have to keep writing the magnitude notation repeatedly. Okay? All right, our second force vector would come from the left cable, and that would be a vector in quadrant 2. And while the diagram has a 30-degree angle to it, we have to express the direction of this vector with respect to the positive x-axis. So what does this angle measure? 100 and... Yeah, 150, right? Okay, now, where's the third vector? Anybody that's maybe taken physics might know.
It's the force of gravity.
Force of gravity acting on the object, pushing it straight down, right? So the third force vector is along the negative y-axis. Let's call that F sub 3. All right, let me back up here. The magnitude for that second force vector, I'll call that the tension of that second cable, T sub 2. And then the magnitude of this third vector is the weight of the box, 1,200 pounds. All right, so think those three forces acting on this box, they're pulling it in different directions, but the sum of those forces combined has to be zero in order for this box to stay still and be in equilibrium. All right, so let's come up with components for the three vectors. So vector f sub 1, its horizontal component would be t1 times cosine of the direction angle 45 degrees, and then the vertical component would be t1 times the sine of 45 degrees. So that tension is a common factor between both components, so I'm just going to write it out in front. T sub 1 times cosine of 45 and sine of 45. And then for the second force vector, the magnitude is T sub 2 times cosine of 150 degrees and sine of 150 degrees. And then F sub 3, again, we know its magnitude is 1,200 pounds. And then what would the angle be associated with that third force vector? Good, 270. So we need cosine of 270 and sine of 270. All right, now, all three of those angles are pretty friendly to work with, right? But typically, the angles for the first two vectors will not be friendly. So I'm going to leave these in terms of cosine and sine, just because that's typically how we're going to have to, okay, rather than simplifying these. Now, the one angle that's not going to change from example to example is going to be the 270. So I will simplify that. I know cosine of 270 is 0, and sine of 270 is -1. So I distribute the 1,200 through here, and I can say that f sub 3 has a horizontal component of 0, and then a vertical component of -1,200. All right, so I think that makes sense. If the vector's going straight down, there shouldn't be a horizontal component associated with it, and then the vertical component has to be negative, right? Okay, so once again, for the object, the box to be in static equilibrium, these three forces acting upon it have to add up to the 0 vector. They have to result in the 0 vector. Now think about how we add vectors together. You add the horizontal components together, you add the vertical components together to get your resulting force vector, right? Well, if this resulting force vector is supposed to equal the 0 vector, that means the components should add up to 0 in both directions, okay? So what we're going to do is create two equations, one for the horizontal components and one for the vertical components. All right, so if I add my horizontal components together, that would be T sub 1 times cosine of 45 plus T sub 2 times the sine of 150. And then the third horizontal component is 0, so of course I don't have to write that in. And these should result in a component of 0. All right, in the vertical direction, it would be T sub 1 times sine of 45 plus T sub 2 times sine of 150. And then minus 1,200 equals 0. Yeah. Did I write sine? Yeah, sorry. Thank you. That look better? Okay. All right, so what did I just create here? Two equations with two unknowns. That's a system of equations. So I need to solve for t sub 1 and t sub 2 in this system. Lots of different ways we could do that. I think the most efficient would be with substitution. Okay? So I'm going to take the horizontal equation here, and I'm going to solve it for t sub 1. That will require me to subtract over t sub 2 cosine of 150. So that'll become negative t sub 2 times the cosine of 150 divided by cosine of 45. And then I'm going to take this and I'm going to substitute it in for t sub 1 in the vertical equation. Now when I substitute it in, I'm going to use parentheses. So that'll become negative t sub 2 times cosine of 150 degrees over cosine of 45 degrees times sine of 45 degrees plus t sub 2 times sine of 150 degrees. And I'm going to move the 1200 over. So this now equals positive 1200. Okay with substitution? All right, now technically what I have here is an equation with two like terms. They both have a variable of t sub 2 in there. But I'm trying to stay exact and not do any rounding in the middle of the process. So I can't combine my like terms here, so to speak. All right? So the trick is treat these t sub 2's like a GCF, a greatest common factor. You're going to factor that out, and what's left will be considered the coefficient of the two terms being combined together. So I'll pull out t sub 2, and then in parentheses I will have the negative cosine of 150 degrees divided by cosine of 45 degrees times sine of 45 degrees plus sine of 150 degrees equal to 1200. And now, to solve for t sub 2, I simply divide over that large set of parentheses. And from here, it's just calculator work. I would suggest if you got a calculator handy, you should try to type it in as I do so. Make sure we get the same value, because a lot of times students will do all the work correctly and they just input it in wrong. All right, so it'll be a 1200 divided by parentheses negative cosine of 45 degrees. Close out those parentheses. Actually, I'm sorry, that's 150. Divided by cosine of 45 times sine of 45 plus sine of 150. And you should be getting 878.5, and the units on this would be pounds because this is a force. All right, so once I got t sub 2, to get my tension in the other cable, all I have to do is take this result and plug it in for T sub 2 up here in this fraction that's circled in blue. Okay, so new calculation here. We'll do the negative of my last answer that I just got times cosine of 150 divided by cosine of 45. And my second tension should be 1075.9 pounds.